I am Anil Kumar. Welcome to my website globalmathinstitute.com and the YouTube channel. In this video, we'll discuss about trigonometric identities. We'll take up a test paper which will have around 9 questions. With these questions, you will understand complete concepts of proving trigonometric identities. Before that, I'll give you the summary of all the relevant trigonometric relations which will be used in proving the trigonometric identities and some concepts. The very first thing which we need to understand is identity is true for each and every value in the domain of the argument. So, there is a subtle difference between trigonometric equations and identities. Equations are true for few values, but the identities are true for all the values of the argument within its domain. To prove an identity, we use trigonometric Pythagorean identities and the basic reciprocal identities. So here is the list of identities which we are going to use to prove the given identities in our question today. So first thing first, as you know, tangent of an angle theta is ratio of sine and cosine. Cotangent is ratio of cosine and sine. So these are quotient identities. And then the reciprocal identities. Reciprocal of sine is cosecant, reciprocal of cosine is secant, and reciprocal of tangent is cotangent. Pythagorean identity, which is sine square theta plus cos square theta is 1. 1 plus tan square theta equals to secant square theta, and 1 plus cot square theta is cosecant square theta. Using these identities, we can actually prove most of the identities. Well, sometimes we do require higher skills for algebraic manipulations. You might need some formulae there also. Example, a plus b whole square is what? Well, it is a square plus 2ab plus b square. A minus b whole square is a square minus 2ab plus b square. And similarly, we have the algebraic identity a plus b whole cube and a minus b whole cube. We can also write a cube minus b cube or a cube plus b cube in factored form as given in the formula right there. These are very useful to prove identities, since we need to simplify one side of the expression and make it equal to the other side. Now, many times I have seen some complicated questions which may require manipulation of the Pythagorean trigonometric identities. As shown here, sine square theta plus cos square theta is equal to 1. That means we could write sine square theta as 1 minus cos square theta. Now, 1 minus cos square theta, difference of square, you remember? A square minus b square is what? A plus b times a minus b. So 1 minus cos square theta can be written as 1 plus cos theta times 1 minus cos theta. We have already got it in the factored form. Now when you have numerator and denominator in factored form, you could cancel and simplify further. You can do the same thing with the other two Pythagorean identities, which are 1 plus tan square theta equals to secant square theta, and 1 plus cotangent square theta is cosecant square theta. You get the idea. So now, there are so many different ways of writing 1 itself. 1 could be written as what? 1 could be written as secant square theta minus tan square theta, correct? Now, secant square theta minus tan square theta can be written as secant theta plus tan theta times secant theta minus tan theta. Now look further. 1 has helped us to relate secant square theta and tangent square theta in many different ways. One more interesting way is that We could even write it as a reciprocal. What is secant theta minus tan theta? It is 1 over secant theta plus tan theta. Do you see the beauty? Now, if you use this way, the Pythagorean trigonometric identities, you can actually solve very complicated trigonometric identities and even equations. So, proving trigonometric identities is actually mastering the skills of using these simple concepts of identities which I have shared with you. We'll explore them further in our test examples. Now, these questions which I have picked up are not simple. They are actually properly arranged so that you also understand the concept of proving trigonometric identity. Let us see how do we solve the test paper now. Here is a practice test paper for you. I would like you to pause the video, copy these questions, solve them out, and then look into my solutions. Let me first share with you the first 4 questions. The question here is to simplify each of the following expression with the technique specified. Question 1. 1 plus tan theta over 1 plus cotangent theta. To simplify this, you can use the technique to write the terms in sine and cosine, and then you can easily simplify it. Question number 2 is 1 plus sine square x divided by 1 minus sine to the power of 4x. You need to simplify this using factoring. Question number 3. 1 minus 1 divided by 1 minus sine x plus 1 divided by 1 plus sine x. Now this can be simplified by taking a common denominator. Question number 4. A square root of 1 plus cos x divided by 1 minus cos x. You can use rationalization to simplify this expression. Now, as you can see, the first 4 questions help you to simplify expressions, and that is extremely important to prove identities. And these are the 4 techniques which are commonly used. Now, let's look into questions 5 to 10. Question number 5. 1 minus cos theta over sin theta equals to sin theta over 1 plus cos theta. Question 6. Sin to the power 6x plus cos to the power of 6x equals to 1 minus 3 sin square x cos square x. Question number 7. Sin square theta plus 2 cos theta minus 1 divided by sin square theta plus 3 cos theta minus 3 equals to cos theta over cos theta minus 1. Question number 8. Sin theta tan theta plus secant theta minus 1 divided by tan theta minus secant theta plus 1 equals to 1 plus sin theta over cos theta. Now these 4 identities will give you good practice on proving trigonometric identities. Here is question number 9. You need to evaluate each of the following terms. In question number 9, we have 1 minus cos theta over sin theta minus sin theta over 1 plus cos theta. In many test papers, many times, we get an expression like this on one side and some other term on the other side. For example, I could equate this to tan 2 theta and then solve the equation. That becomes a question. So in that case, you have to find the value on one side and then solve the equation. So these two are from that point of view. Question number 10 is sin theta over secant theta plus tan theta minus 1 plus cos theta over cosecant theta plus cot theta minus 1. So both these can be evaluated and you will get a real number as its solution. So now let's begin solving these one by one. Let us see how do we solve, rather simplify in this case, an expression using different techniques. So first one is 1 plus tan theta over 1 plus cotangent theta. We need to do it using sine and cosine. So tan can be written as sine over cos. So I could write this as 1 plus sine theta over cos theta divided by 1 plus cos theta over sine theta. Now, cos theta can be taken common. So we get cos theta plus sine theta over cos theta equals to sine theta plus cos theta over sine theta. Now here you can clearly see that cos theta plus sine theta cancels, and therefore it simplifies to 1 over cos theta divided by 1 over sine theta, which can be written as sine theta over cos theta. And therefore the given expression is equal to tan theta. Now let's simplify question number 2 expression, which is 1 plus sine square x over 1 minus sine to the power of 4x. Now denominator can be written as difference of squares. So we have 1 plus sine square x in the numerator divided by, this can be written as 1 plus sine square x times 1 minus sine square x. You can cancel 1 plus sine square x. You get the term 1 divided by 1 minus sine square x. And that is equal to 1 over cos square x. So that is how we could simplify this one. And if you want, you can write this as equal to secant square x. So in this case, we have used the Pythagorean identity cos square theta plus sine square theta equals to 1. So we could write cos square theta as 1 minus sine square theta, correct? Let's take up question number 3 now. 1 over 1 minus sine x plus 1 over 1 plus cos x. We can take a common denominator and then simplify it. So taking common denominator is multiplying 1 minus sine x with 1 plus sine x. Cross multiply and you get 1 plus sine x plus 1 minus sine x. So that gives you 1 and 1 as 2, sine x and minus sine x cancel. So we get 2 over. Now this is difference of squares. So 1 minus sine square x. And as we did earlier, 1 minus sine square x is cos square x. So that is equal to 2 times secant square x. Question 4. Square root of 1 plus cos x over 1 minus cos x. To simplify this, we'll rationalize. We'll rationalize the denominator. So we can multiply and divide by 1 plus cos x, square root, both numerator and denominator. So in the numerator, we get 1 plus cos x square root whole square, which leads to 1 plus cos x. And in the denominator, we get 1 minus cos square x within square root. And that gives you 1 plus cos x over square root of sine square x. Now this is 1 plus cos x over sine x. So you could write this as 1 over sine x plus cos x over sine x. Or this can be now written as 1 over sine x is cosecant x plus cos over sine is cotangent x. So that is how we can actually write this particular expression. Here are 4 important techniques which you will need to prove trigonometric identities. They involve writing trigonometric ratios in the form of sine and cosine. They involve factoring the given expressions, rationalizing them, and also sometimes taking a common denominator and then working with. Our first 4 examples are based on these concepts. So understand these concepts while solving the test questions. Now, let us see how do we prove the identities. Question number 5 is 1 minus cos theta over sin theta is equals to sin theta over 1 plus cos theta. We can start from left side or right hand side, and in this particular case I will use the strategy of rationalizing, right? And this time we'll rationalize the numerator starting from the left hand side. So if I take the left hand side, which is 1 minus cos theta over sin theta, I could multiply and divide by 1 plus cos theta. So we get what? So when you multiply and divide by 1 plus cos theta, in the numerator we get difference of squares, which is 1 minus cos square theta, and in the denominator we get sin theta times 1 plus cos theta. Correct? The numerator is equal to sine square theta. Square theta. Let's divide by the denominator sine theta times 1 plus cos theta. So what we see here is that we have a part of denominator which is 1 plus cos theta, and now once you cancel away one of the sine thetas, we get the right hand side, which is sine theta over 1 plus cos theta. Is that clear? So that is how you prove an identity. You start from one side and prove it to be equal to the other side. Question number 6. Sine to the power of 6x plus cos to the power of 6x equals to 1 minus 3 sine square x cos square x. You can pause the video, answer this question, and then look into my suggestions. The method to do this is look into this expansion of a cube plus b cube. A cube plus b cube is a plus b times a square minus ab plus b square, correct? So that is what we could do. So let me rewrite the left hand side as a sum of cubes. So we could write sine to the power of 6x as sine square x whole cube. So that becomes sine to the power of 6x. Similarly, cos to the power of 6x can be written as cos square x whole cube. And now we can expand it using the standard formula. So it becomes sine square x plus cos square x. Now that's a Pythagorean identity, which is 1. So that is why it is very important to write higher powers in this particular form. The other expression will be square of sine square x to the power of 4 minus product of these two, which is sine square x cos square x plus cos to the power of 4x. Now the first term is equal to 1 using the Pythagorean identity. And now in the second term, we could again write this as sine square x plus cos square x whole square. Correct? But then for that, we need 2 sine square x cos square x. But we have 1 minus. You get the idea. So we can add and subtract 2 sine square x cos square x. So let me show you how. We have sine to the power of 4x minus sine square x cos square x plus cos to the power of 4x. Now, to this, we are going to add 2 sine square x cos square x and subtract 2 sine square x cos square x. Same term is being added and subtracting, so we are not changing the expression, right? But it helps us, since now you can see that we can actually combine these terms, and using these three terms, what can we write? Well, that is written as, let me put a square bracket here, sine square x plus cos square x whole square. Get the idea? So this is sine square x plus cos square x whole square. So when you expand, you get sine to the power of 4x plus 2 sine square x cos x plus cos to the power of 4x. Perfect. And what remains is these two terms, and they can be combined to write minus 3 sine square x cos square x. Correct? And therefore, we can now write this as 1 minus 3 sine square x cos square x, which is the right hand side as required. So that is how you can prove this identity. So I hope the steps are absolutely clear. Very good example from test point of view. Here is question number 7, another very important question. I have seen this question many times in previous test papers. Now there are many ways to solve this. What we could do is we could simplify and write sine square x as 1 minus cos square x and write both these terms as a quadratic in cosine. So that is a strategy which I am going to now use. So we'll begin with the left hand side, which is given to us as equal to sine square theta plus 2 cos theta minus 1 divided by sine square theta, this is 3 times, plus 3 cos theta minus 3. So writing sine square theta as 1 minus cos square theta plus 2 cos theta minus 1 divided by 1 minus cos square theta plus 3 cos theta minus 3. Now 1 and minus 1 will cancel, correct? And we are left with minus of cos square theta plus 2 cos theta divided by, and here 1 minus 3 will give us minus 2, right? So we have minus cos square theta plus 3 cos theta minus 2, correct? We can take minus cos theta in the numerator common, which gives us cos theta minus 2 in the denominator. Let us first take minus common and then we'll factor this, correct? So we'll take minus common. I prefer to write this with positive coefficient. So it is cos square theta minus 3 cos theta plus 2. So we can now factor this. We need product of 2 and sum of minus 3. So minus 2 minus 1 can work. So we can write this as minus cos theta. Minus and minus I'll cancel. They get cancelled, correct? So what we have in the numerator is cos theta times cos theta minus 2 divided by, factoring this out, we get cos theta minus 2 times cos theta minus 1. So now the common factor cos theta minus 2 can be cancelled. So we get what is required given in the right hand side as cos theta over cos theta minus 1. Perfect. So that is the solution for question number 7. Let's move on and take question number 8 now, which is tan theta plus secant theta minus 1 divided by tan theta minus secant theta plus 1, and that should be equal to 1 plus sin theta over 1 plus cos theta. We can begin with the left side and simplify it. Now, I will use a very special technique here to solve this. You remember that 1 plus tan square theta is equal to secant square theta, correct? Now, we can reorganize and write what 1 is equal to. So, 1 is secant square theta minus tan square theta. The difference of squares for secant and tangent. So, I am going to replace this 1 with the difference of these two. And then we'll factor this out and rewrite our expression. So very special technique which I am going to share with you now. So we'll begin with the left hand side, which is tan theta plus secant theta minus 1 over tan theta minus secant theta plus 1. So in this case, I am going to write the numerator minus 1 as explained. So we have tan theta plus secant theta. You could also expand this. Either one could work for you, right? So minus of secant square theta minus tan square theta divided by tan theta minus secant theta plus 1, correct? Now the numerator, as I was saying, this can be factored out. So if I factor this, what do I get? I get tan theta plus secant theta minus secant theta plus tan theta times secant theta minus tan theta. You get the idea. Divided by, we have tan theta minus secant theta plus 1. Now, as you can see, tan theta plus secant theta is a common factor, correct? So we are using this as a common factor to factor. So we get tan theta plus secant theta as a common factor. So we get 1 here minus the other term, which is secant theta minus tan theta, divided by tan theta minus secant theta plus 1. And now when you open this bracket, you get 1 minus secant theta plus tan theta. You see that? So they cancel out. So these terms cancel. And therefore, you are left with tan theta plus secant theta. Tan theta plus secant theta, so I'm just writing 1 here. Tan theta can be written as sine over cos, and secant is 1 over cos, correct? One over cos theta. And that is equal to the right hand side. As you can see, we have cos theta as common, and the numerator we have sine theta plus 1, and that is the right hand side. Do you see how we can prove this identity? In this test example, you see the beauty of using the Pythagorean trigonometric identity. 1 plus tan square theta is secant square theta, which can be written in many different ways. And see how we wrote 1 as difference of sine square theta and tangent square theta, factored it, and then proved the identity. That's the beauty. So strategy which I have utilized here is to write 1 as difference of secant square theta minus tan square theta. Now here is question number 9. In this question, you need to evaluate each one, right? So we are not given what is this equal to. Let's figure it out. So we have 1 minus cos theta over sin theta minus sin theta over 1 plus cos theta. Now to do this, we can actually cross multiply taking the common denominator, and then we can solve it, correct? So we can write this expression as equal to taking common denominator of sin theta times 1 plus cos theta. Cross multiply, we get 1 minus cos theta times 1 plus cos theta minus sin square theta. Now here, the first term will be difference of squares, so we get 1 minus cos square theta minus sin square theta over sin theta times 1 plus cos theta. Now we can take minus common, so we get what? We get 1 minus cos square theta plus sin square theta, and the denominator being sin theta times 1 plus cos theta. Now sin square theta plus cos square theta is 1, and so in the numerator we have 1 minus 1 over sin theta times 1 plus cos theta. 1 minus 1 is 0, and therefore the value of this expression is 0. So that is extremely important to understand. We can actually combine this with trigonometric equations. So important to note here is this can be a part of solving trig equation. Okay. Question number 10 is also on the same basis. Slightly more difficult. So I'll say this is a challenging question for you. You need to evaluate what is sine theta over secant theta plus tan theta minus 1 plus cos theta over cosecant theta plus cot theta minus 1. So in this expression, you can write sine. You could use the strategy of writing 1 as difference of squares as we did, or you can just convert sine, secant and tangent in sine and cosine. So let's convert them into sine and cosine. So in that case, what do we get? So the first term is sine theta divided by secant is 1 over cos plus sine theta over cos theta minus 1 plus here we have cos theta over 1 over sine theta plus cos theta over sine theta minus 1. So in the first expression, you need sine theta, cos theta is in the denominator. I can take it up and we can write this as sine theta cos theta, and the denominator becomes 1 plus sine theta minus cos theta, correct? In this expression, sine theta is the common denominator, it gets multiplied with minus 1. So we get here cos theta sine theta divided by 1 plus cos theta minus sine theta. Is that clear to you? So that is how we have simplified this particular expression. Now here you notice that we have kind of difference of squares, right? So we could write this as 1 plus sine theta minus cos theta and 1 minus sine theta minus cos theta. Let me rewrite this to show you. So we have sine theta cos theta in the numerator divided by, I can write the first term as 1 plus sine theta minus cos theta, and here sine theta cos theta is in the numerator. I can write this as 1 minus sine theta plus cos theta, correct? And then we can take that as a common denominator. So what do you get? You get 1 square minus sine theta plus cos theta whole square in the denominator, the product of these two. And in the numerator, you can cross multiply these. You get the idea. Correct? You can cross multiply these. So you get this less space here. So let me rewrite this right here. So we have, or we'll just factor out sine theta cos theta, right? So we'll factor out sine theta cos theta. And the denominator, we have 1 minus sine theta plus cos theta whole square, multiplying these two. And here we cross multiply, since we factored it out. We have here 1 minus sine theta plus cos theta, and here we have plus 1 plus sine theta plus cos theta. You see that? Now in the numerator, 1 and 1 becomes 2, and when you subtract sine theta plus cos theta and add, that is 0. So now what you really get is In the numerator, you get 2 times sine theta cos theta. Correct? So here you get, let me rewrite here in a different ink so that I could squeeze it in. So I'll rather move it a bit. So here we get 2 times, let me show you how exactly. So this term plus and minus cancel. So 1 and 1 is 2. So let me rewrite this as sine theta cos theta times 2. Clear? Divided by, we have 1 minus, let us expand this. We get sine square theta plus cos square theta plus 2 sine theta cos theta. Clear? So in the numerator, we have 2 sine theta cos theta, and in the denominator, we have 1 minus, and within bracket, sine square theta plus cos square theta is 1 plus 2 sine theta cos theta. Clear? 1 and minus 1 cancel, and so we could rewrite this as 2 sine theta cos theta divided by 2 sine theta cos theta, and this is equal to 1. Perfect. So that is how we could evaluate this expression, and it is equal to 1. So I hope this solution is absolutely clear. These are, I should say, one of the best set of questions on this topic of trigonometric identities. To begin with, we learn how do we simplify the expressions using the techniques of writing the terms, the secondary ratios in terms of sine and cosine, even tan in terms of sine and cosine. Other technique was to factor, then to take common denominator and rationalize. In proving the identities, we use these techniques and we prove the identities. We also took examples which are seen in many questions where a part of the question is to prove the identity and the other part is to solve the equation. So we have taken it as question number 9 and 10, which makes it very important. I hope that helps. Feel free to write your comments, share your view, and if you like and subscribe to my videos, that'll be great. Thanks for your time and all the best. I hope you enjoyed watching this video and learning as well. Feel free to write your comments, share your views. If you like and subscribe to my videos, that'd be great. Thanks for your time and all the best.